welcome to Source Code, an online program hosted by the American Computer and Robotics Museum here in Bozeman. We're so glad you could join us on Zoom tonight. Doug's resume reads like an adventure novel. He began his career at Grumman Aerospace, where he contributed to 4 successful Apollo missions, and later he helped lead the flight test and development program for the Navy's F-14 fighter aircraft. Inspired by this early work exploring the limits of human performance, Doug went on to earn advanced degrees in engineering, biochemistry, medicine, and biomedical engineering. As a postdoc at Johns Hopkins, he invented an innovative open heart research procedure, and at Travenol Labs, he developed a wearable drug delivery device for cancer patients. He has been a healthcare director, a president, a CEO, and a board member for a veritable who's who of companies operating in the healthcare space. And in 1993, he started his own consulting practice and devoted 25 years to integrating medicine, technology, and business for healthcare companies. Though Doug has many, many stories he could tell, tonight he'll be sharing about those early years with the Apollo program. So please join me in welcoming Doug Munch.
Wow. Thank you, Eleanor. It's such a kind introduction. I really appreciate it. So tonight, first, I would like to thank both Barbara and Eleanor for inviting me to be the first speaker in the seminar series, Source Code: Stories from the Cutting Edge. It's really quite an honor to be here and to be able to present this information to you. And hopefully we'll all find it exciting as I relive some of these things. First, I'd like to make a disclaimer. I am not an astronaut, although at one time I went down to Houston with the intention of doing that, but that's another story. So I did not literally journey into space. However, let me say that every person who worked on the Apollo program or any of the projects lived every mission, and we were all intimately involved. So in a sense, we did all have experiences in space together as a group of engineers and scientists and people who were involved one way or another with these programs. In tonight's seminar, I'm going to tell you some stories, and I'm going to tell you stories that didn't necessarily make the news, and often the intensity of the stories that did make the news didn't correctly portray what was going on and the angst that was felt on the ground by the people who were working on the program. I'm going to share with you some personal experiences in the computer world. After all, we're a computer and robotics museum, and also in the source code development world for these missions. I'll talk about Apollo mission stories based on firsthand real-time observations on Apollo 11 and 12, and on personal involvement on my role on Apollo 13 that had the explosion. At the very end, I'll probably summarize a little bit about the legacy of the Apollo program. So as Eleanor indicated, my first job out of college with a degree in chemical engineering was to work at Grumman Aerospace Corporation. And Grumman invited me to have a choice between 2 opportunities. One of them was in manufacturing, which sounded interesting but not exciting. And the other was on the Apollo program to work on the lunar module. And I thought that sounds really exciting. And here I can make a contribution. I certainly would hope I can make a contribution at any rate. The job that they gave me was to work in the environmental control system, known as ECS, and to be a thermodynamic systems engineer. That's pretty technical stuff. I'll explain a little bit about that later on. What really struck me many years later was that thermodynamic systems engineering in the environmental control system was really biomedical engineering. And as Eleanor indicated, later on, I ended up with a doctorate in medicine and biomedical engineering. So this was something that really put me in that direction to move forward. Because we are a computer museum, I need to tell you about the IBM 36075 operating system, because this computer was the core of all of the computations for our thermodynamics group, but also for all of the other subsystems on Apollo. And when I say subsystems, I mean things like reaction control system, which controls the motor, the engines, the rocket motors. It could also mean the landing radar. It could mean the radar to hook up again with the command module. So all of these were parts of the total operating system. The IBM 36075 was introduced in 1965, and it was a third generation computer, but it was the first general purpose computer. So what does that mean? General purpose means that this computer could deal with scientific problem solving as well as commercial problem solving. It was a mainframe, so it was enormous. You'll see just in a second. The input to this computer came from mainly one source, and the computer input that we used was punch cards. And I'll tell you about punch cards as we go along. The output could be in the form of magnetic tape. So if you think of the days where we had magnetic tape for music recording and playback, it was exactly the same kind of magnetic tape, except it recorded a digital code. And on the thermodynamics side of the world, the output that we got was green paper. And I'll show you some of this stuff as we go along as well. The core of this machine was magical. It was a magnetic memory. And the magnetic memory was made up of iron oxide rings, as you see here. And there was a small wire that went through each of these rings. If the current went through in one direction, the ring was positive. If it went through in the other direction, the ring was zero. As many of you may know, computers only understand zeros and ones. So a magnetic iron magnetic ring was perfect because it was binary. The computer had 128 kilobytes of memory, by today's standards, minuscule. And it provided 8 kilobytes to a maximum of 1 megabyte of main memory. If I told you you could buy a computer today with this much memory, you would laugh. The clock speed on this computer was 1.024 megahertz. So I'm kind of talking to some of the computer geeks out there. Was at the time amazingly fast, but by today's standard, it was slower than a turtle. And so this was the operating system that we used. The weight of this system, if you want to take a guess, think for a second how much you think of what a system like this would weigh. It was 610 pounds. And this is a photograph of Houston's enormous computer machine room. Houston had 5 of these machines. They all worked in different purposes, but in this one, here's a machine, one of the 5 machines that was used down south. You could buy this whole system for a mere $5.5 million. And that would be in 1969 money. So if you use the Federal Reserve inflation calculator, which I did, and said, how much is $5.5 million worth today? You'd have to spend $44 million for this system that we used. And Grumman had a similar system up in Bethpage. The system that we had, we didn't buy from IBM. We rented it from IBM. It cost $115,000 a month to rent this thing. And today, that would be equivalent to about $1 million a month. Let me give you an idea about what that was at the time, even at $115,000. An engineer's pay was less than $1,000 a month. When I started at Grumman, I started at $9,800 a year. It sounds preposterous, but if you inflation adjust that number, it was apparently, which is news to me today, of $87,000 a year. So $9,800 a year was a lot of money as an engineer in those days. In fact, let me go back here because there's a couple of things I want to show you. And here in this corner, you can see this is a central processing unit. This central processing unit had no screens, no keyboard, but this was the master control for the computer. And this computer operator was responsible for making this thing work correctly. In this other lower corner here, right here, we can see some other things. These are boxes of punch cards down here, and these bunches of punch cards contain computer source code. Those punch cards are put into this machine, and you see a stack of them right here, and they run through the machine, kind of lickety-split, coming out on the other side. And this is the source code that the computer uses in order to run its computer program and get us the scientific and engineering results that we were looking for. So here are punch cards. There is a history to these things. Maybe some of you have seen these before. This is a Fortran statement card, which means that when we put code into the machine, it was punched out 80 columns wide and 9 or 10 columns deep. So there's an interesting history here. Punch cards actually started in the late 18th century, so that's the late 1700s. They were used in cloth making machinery and looms for the purpose of putting design into the fabric. 100 years later, a guy named Herman Hollerith came around, and he became interested in statistics. As he was interested in statistics, he ended up with a PhD in statistics, and his thesis was a model for computing statistics. He was a professor for a while. He ended up with the Census Bureau in Washington, D.C. And his ideas of computing were originated and inspired by train conductors, because in those days, train conductors used punch cards to punch information into the card about what station you were getting off at, perhaps what you paid for the ticket, and then there was a permanent record. So that inspiration led to his method for compiling statistics and his work that ended up going at the Census Bureau. In 1884, he submitted a patent called The Art of Compiling Statistics, and that patent was issued in 1889, 5 years later. In the patent, he describes fields which have become known as Hollerith fields. Hollerith fields are alphanumeric, alpha meaning letters of the alphabet, numeric meaning number information. And some examples of that, these fields could contain age, employee ID, sex information, date information, quantity, that could be something like number of children. So you see for a census, this could be very interesting, and they could be sorted. So if you had state information there, you could sort these computer programs, these kinds of cards, by state and find out how many people were in different states, how many in different cities. The use of these cards saved the Census Bureau $5 million back in 1890 and 2 years worth of labor. That $5 million would be worth $177 million today. But remember that the population of the United States at that time was probably around 50 million. These cards also had, and you can see these holes. Where these holes are punched, there was a piece of paper that was punched out in the back. These little pieces of paper that were punched out in the back were called chips or chads. And most of you will remember in the 2000 election between Bush and Gore, there was a big lawsuit that took place over hanging chads. And these were the punch cards and the pieces of paper that didn't punch cleanly all the way through. The other thing that we get from the punch card era is the expression, do not fold, spindle, or mutilate. And so I'm sure some of you have used that expression one way or another in your life. The important part of this is ultimately becomes the source code. And this is a binary representation of a number. So I'm going to talk with you about source code, and this number is 1969, the year of the Apollo mission. In those years, the source code that we used was Fortran 4. It was a highly automated, highly sophisticated computer code for programming science. The computer was designed to take this high-level code, which was closer to writing equations, and convert it into binary that you see up here. In the environmental control system, we used a mathematical model called forward differencing. So this is personal experience that I'm talking about here. And the thermal model was we used an analogy of an electrical resistance capacitance circuit. So what does this mean? I'm not going to go too deep into the weeds with this because it gets really confusing. But here we can look at, and so for those of you who have an engineering or physics background and are familiar with Kirchhoff's laws, in the electrical model, you have voltage, current, capacitance, and conductance, which tells us the relationship between these in a circuit. In a thermal model, we have temperature, heat flow, which is the same as current. We have heat capacity, which is the same as capacitance, and thermal conductivity, which is like conductance. Heat capacity, we all have experience with conductance one way or another, because if you put an aluminum fry pan on your stove and the handle gets hot, that's because of conductance. And if you put an aluminum fry pan on the stove that has a stainless steel handle, the handle doesn't get nearly as hot because stainless steel doesn't have the thermal conductivity of aluminum. So if you start looking at these kinds of properties, you can actually program something like this. Now, this is a nodal network, and this happens to be a resistance capacitance network. If you take this and multiply it by 1,000 times, this is what the mathematical model for the lunar module looked like as we were trying to figure out what kinds of temperature extremes the astronauts might experience during flight. So these RC circuits are actually pretty important because they show up in things like intermittent windshield wipers on your car, traffic lights that stop, at intersections, pacemakers for people who have sick hearts. So all of this mathematics really is for a reason, and it was very important. So how do we get this mathematical stuff into the computer? Well, the way you get it in is with key punch operators. This lady on the left takes a stack of blank key punch cards and she puts them into her machine and they feed one by one into this location. Here she has an 11 by 14 size coding sheet, and this coding sheet is 80 columns wide and maybe 14 or 20 columns deep. So she types each row, the 80 columns in each row into the punch card. When that punch card is done, it moves over here. She gets a stack. And when she's done with this sheet, she hands the punch cards and the sheet to the next key punch operator. This lady punches exactly the same code, but she's not punching holes in the card. Her key punch machine has a light underneath it, and the light is detected. And if it detects correctly, the card goes on because it indicates the holes are in the right place. If the hole is in the wrong place, a buzzer sounds and she has to pull that card out, check the code that's on the card versus what's on the sheet, and maybe even give it back to her for retyping. So it could be, as you can imagine, an extremely cumbersome process. Once the cards are typed, they're put into a cardboard box. Pretty sophisticated technology. In the cardboard box, these cards would all be the Fortran program, the instructions for the computer that would go back into the computing center to be run. So the cards contain Fortran instructions, and they also contain the alphanumeric fields that we called Hollerith fields that I mentioned earlier. The Hollerith fields contain documentation. They contain sequence numbers. This was important because if you dropped a box of cards and they weren't numbered in sequence, how do you put them back together? That means that you have to have the key punch operator completely repunch that deck of cards. And there's a lot of very unhappy people. The other thing you can put onto these cards in the Hollerith fields are comments. And we'll see later, many computer programmers, as getting bored with what they were doing, decided that they would add jokes to those cards. So then, as we saw earlier, the cards end up over here, and then this guy here, who's the computer operator, puts them into the cards into the machine to be read. For some output, we didn't want our output in the form of punch cards. We'd never be able to figure it out. So in thermodynamics, we got our output in the term of computer paper with these green and white striped bars. And we got probably 4 or 5 stacks of computer paper, 4 inches deep. And these are 11 by 17 sheets. So there was a lot of information, and we had to know what node in the network we were looking for to see whether it was within specifications. It took, just so another piece of random data, it we would deliver the punch cards over to the computing center at 5 o'clock at night when we were done with our shift, and it would take all night long to run our thermal network on the fastest computer on Earth, all night long. Your computer would do way faster. So the other computer that was important, because the computer I just told you about was on Earth, this computer was not. This is the Apollo guidance computer, and this is called a disk key. The Apollo guidance computer we have this in our museum. So if you visit the American Computer and Robotics Museum, you will see one of these as an example, and the disk key. So let me tell you what this is. NASA needed something that was lightweight and robust enough to do tasks like calculate the lunar landing, calculate guidance, calculate parameters for the environmental control system, calculate things for the reaction control system or the rocket motors that were on board. There were 2 of these computers in space. One was on the lunar module, and the other was on the command module, which was circling the moon. They ran completely different sets of software because they had completely different missions. These computers were vastly underpowered by today's standard. But considering how vastly underpowered they were not at all simple. And they were so important, in fact, that the crew considered the computer to be the 4th crew member. The fellow who designed all of this hardware was a guy at MIT named David Haag. And he was a hardware developer. And so he put all of his effort into putting this thing together. This computer had specifications. So again, this is more for the computer geeks among us who are here. The weight of this computer was 79 pounds, about 32 kilograms. Now, this is lightweight, right? And we'll see in a minute just how lightweight. The computer speed, the clock speed was again about 1.24 megahertz, and it could calculate between 50 and 100,000 instructions per second. To land the lunar module on the moon, it needed to be able to calculate 85,000 cycles per second, or instructions per second. It had a read-only memory of 4 kilobytes, not even megabytes. Your cell phone photos are way larger than this. It had a read-only memory, which was fixed, of 72 kilobytes as well, and this was not erasable. It was 16-bit magnetic rope memory, and also called LOL memory. And so what is rope memory? Rope memory are the magnetic beads I told you about earlier with the copper wire through them. So the current in one direction was +1 and in the other direction was 0. Why was it called LOL memory? Well, this was a joke that the computer programmers used to use, because these memory modules were made up by old women all by hand, so it was little old lady memory, referring to the fact that the women were making these computer modules by hand. There were 32 modules that were addressable using the disk key, and the price of this thing was unknown because it was done at MIT and we had no idea what the price was. They were just contracted to go ahead and do this. So for the computer geeks among you, you can read this stuff. I just want to go to the bottom here, because the computing power, if we say that the Apollo guidance computer had a computing power of 1, was 4 million times less powerful than your smartphone. 4 million times. I think when you think about the weight as well, the Apollo computer was 70 pounds, and your cell phone is about a third of a pound. So the source code for the guidance computer had to be developed. So if you're facile with your binary coding, you'll know what this says. And you'll see that it's much easier to write this in an alpha form. This spells hello with an exclamation point at the end. So you can see it's very inefficient. When I was doing medical research at one point, I was actually coding in binary. And if I had to do that today, it would be impossible. But in those days, it was something that we had to learn for the kinds of computers that we were using in order to process our data. This source code was developed at MIT by a team directed by Margaret Hamilton. She was brilliant in the source code development, and especially in this very special version of assembly language. The assembly language converts the source code into binary, zeros and ones, so the computer can operate on it. The assembly language was the backbone of the Apollo guidance computer, and the Apollo guidance computer had 72 kilobytes of space. That's all. And that 72 kilobytes of space had to control all of the aircraft operations. The code was incredibly compact. And just to give you a bit of a historical note, years later, Microsoft and Intel had a huge war about which was more important, hardware or software. Of course, it ended up being basically a wheel rolling forward because software became incredibly inefficient as opposed to this, which was a very compact and unbelievably efficient. And hardware had to get bigger in order to accommodate the larger source code. This is what source coding looked like. And it had a ton of Easter eggs in it, as I mentioned before, because the programmers would put jokes into it. The ignition subroutine, as an example, was subcoded burn, baby, burn, with references to the engine burn sequence, timing, and power controls for the rocket motors. The subroutine that controlled the disk key, which we saw as the buttons that were pushed, had a name called Pinball Game Buttons and Lights. So they put a little bit of humor into this. And even Shakespeare was quoted in some of the comments for the use of verbs and nouns because the disk key worked by understanding a verb and a noun. Meet Margaret Hamilton. Oh, I'm sorry. This is the wrong Margaret Hamilton. This is Margaret Hamilton from The Wizard of Oz in 1939. Wrong slide. Here we go. This is better. So this is Margaret Hamilton, who was at MIT in 1961 at the age of 25, writing source code. This is a photograph of her proudly displaying an MIT flag. And this is a photograph of her at age 33 in 1969. And this stack of paper is the 72 kilobytes of Apollo source code. Can you imagine? This ran the computer program for the lunar module. Later, she became director of the software engineering lab at MIT. And she was the one who coined the word software engineer. I want to talk a little bit now about the actual missions. And on Apollo 11, there was prophecy. Some of these stories maybe you have not heard. So I'm going to talk about things that were prophetic. Buzz Aldrin, because he was going to be the command module pilot, had to be familiar with the computers because that was his job. So he went up to MIT and he talked to Margaret and he said to her, I want information, a certain amount of landing information to be available in the computer. he wanted to have information from the rendezvous radar, which was used in order for the lunar module to connect back with the command module. Little did he know, it never got programmed in. There wasn't enough space in the computer to put this information in, but Buzz was never told about it. This becomes prophetic as we move along here. 5 days before the Apollo 11 mission that we're talking about here, there was a simulation run by the engineers with all of the computer specialists who were in mission control. It was a practice session, and Richard Coos, who was the NASA simulation engineer, put in a code that was number 1202. Nobody knew what this alarm was for when the alarms went off. Coos was really upset. As punishment, those engineers in the NASA Control Center had to put in 4 hours of more training to learn about the program alarms. There was one additional piece of prophetic information that took place, and that was a pre-flight press conference. This was a press conference with Neil Armstrong, and Neil was asked, if you could take one more thing to the moon with you, what would it be? His answer was more fuel. And we'll see how these things play out as we move along. So I want you to see here, this is the control board inside the lunar module. Here's the window. So Neil Armstrong, so this is a dummy. This is not Neil, but Neil Armstrong would be looking through this window. And if you look really closely, you can see that this window has a bunch of markings on it. The markings were at a height calibrated to the height of the commander, so that when he looked through here, he could look and he could tell angles for horizon as well as up and down. This became very important on Apollo 13, which I'll tell you about. The disk key that Buzz Aldrin would use was down here. So he would be able to punch in a verb and a noun here, and like 0616, and by that he could display the velocity of the lunar module in this little panel. So you can see it was incredibly complicated. On July 20th, 1969, the lunar module is descending from 3,000 feet above the surface of the moon to 2,000 feet above the surface. All of a sudden, and Buzz is, and I should tell you what Buzz is doing, because Buzz is there. Now, he's already requested stuff that they're not going to use. He said, I want the computer to tell me about what happens if we have to have an abort and we have to ascend back up to the command module. So he had the ascent radar in standby. What he didn't know is that the rendezvous radar, which controlled the ability of the lunar module to reconnect with the command module, had a bug in it. And this bug added 15% computing capacity to the already stressed out guidance computer. And then he punches in that he wants landing information, so he knows where he is relative to the surface, verb 16, which is display, and noun 68, which means land. So he punches this information in, and now the computer is really stressed. And then he put in an eighth command. The computer said, I can't do this. And an alarm sounds. And the alarm that sounded was a famous 1202 alarm, which is a computer overload. Fortunately, the guys in Houston had trained for this. And now, because they had the extra 4 hours of training, they knew what this alarm was. And they were able to handle it. So NASA's response was 2 engineers, Steve Bales and Jack Garman, and Jack communicated back to the lunar module, keep going, because he knew that the computer was programmed to automatically reset when it would get overloaded. This was a stroke of genius by Margaret and her team, that if the computer got overloaded, it would default to the highest priority program at the time. So with code 1202, it said, we can't deal with this. We're going to reprogram. And it reprogrammed the computer, and they kept going. 5 times between 3,000 feet and 2,000 feet, the computer overloaded. And 5 times it automatically reset. And Buzz was very thankful because he was clueless about what was going on. So there are 4 other stories that I want to tell you about on Apollo 11. Neil flew the lunar module down to the surface. Was he supposed to? No, he was not. The computer was supposed to fly the spacecraft down to the surface, and there were early games that came out on computers, the lunar module game, and that lunar module game could fly the simulated lunar module to the surface, and you could override it like Neil did and crash most of the time until you figured out how to follow the flight path. The communication between Earth and the lunar module was very spotty. That kind of stuff, right? So Neil used that to his advantage, at least the way I heard the story and experienced the story. He goes, we had spotty communication. I can't hit you. I'm switching to manual. Well, he was a test pilot. He wanted to fly this thing to the surface anyway. So he's coming down to the surface. At 60 seconds, NASA has a verbal communication to the Apollo that says 60 seconds. It's short and contrite, but it's packed with meaning because it means in 60 seconds, you are out of fuel. If you're not on the surface in 60 seconds, you have to abort. So this is called bingo fuel in the space program. It has a little different meaning in Navy, but bingo fuel meant you are out of fuel, and if you're not on the surface, you hit the abort button and you get back to the command module. And at 60 seconds, he's still 100 feet above the surface. So now 30 seconds are left. Another message from ground control. And it was 30 seconds to bingo, right? 30 seconds worth of fuel. He's still 60 seconds above the surface of the moon. He's flying around. He's looking for a flat spot because the moon was full of boulders in this location. And he had to find something that was flat to land on. We believe, because the information that we had available to us, is that he landed at Tranquility Base with 15 seconds of fuel left. The folks on the ground said, "We're turning blue. Can we breathe now?" And of course they could, because he was at Tranquility Base. The Eagle had landed. Just to give you an idea of the amount of stress that he experienced during the descent. Well, and if we sit in a chair and we're resting, our heart rate probably should be 80 beats per minute or less. During the normal portion of the descent, his heart rate was 110 beats per minute. We had this telemetry data. When he lands with 15 seconds of fuel rate left, his heart rate is 156. That's zone 4 for those of you who are exercise fanatics and work out. His heart rate was up at a zone 4 level just because of the stress of trying to find a place and not run out of fuel in the process. So now they're on the surface of the moon. They're going to go walk around on the surface. They're putting on their backpack. And as they're putting on their backpack, Neil turns around inside the cabin of the lunar module and he breaks off the toggle switch that arms the ascent engine. So what does that mean? That means that with the toggle switch broken, they're going to have to find some way to arm the engine so that they can get back to the command module, or they're forever stuck on the surface of the moon. So how does Neil respond to that? He looks at Buzz, he says, "We'll fix that later. Let's go on a moonwalk." And out the door they went on a moonwalk. So they do their walk around on the moon, and there's all kinds of stuff going on. They get back into the lunar module. And meanwhile, NASA has been working on some complicated solution to work around the broken toggle switch, but they have to sleep. Now they sleep in their spacesuits. And why do they sleep in their spacesuits? Well, in case a small meteorite penetrates the very thin skin of the lunar module will decompress, but you don't want the guy's spacesuit to decompress or they're dead. So they sleep in the spacesuit just in case there's a decompression. In the morning, Buzz wakes up and he's soaking wet. He's a very unhappy camper. And in fact, he's kind of camping on the surface of the moon, but in a spacesuit. And so he screams back at Houston, "Why am I soaking wet?" And Houston asks him a question. They said, "Well, when you came back last night or yesterday from your EVA, your extravehicular activity on the moon, did you reset the temperature of your air conditioner on your backpack?" And Buzz said, "No, why should I do that?" And they said, "Well, because when you went to sleep, you were still set at a temperature that would keep you cool when you were exercising on the moon. But when you were asleep last night, your metabolism dropped and the temperature dropped below the dew point in your spacesuit and it rained on you." So again, he was embarrassed, not happy camper, but he saves the day. So it's time for them to return to the command module, and Buzz took his Fisher space pen, which you can buy today, and he took the cap of it, and he took the cap of the space pen, and he flipped the circuit breaker toggle switch, it armed the ascent engine, and up they went. It was really quite a day. So you can see that even on Apollo 11, there was plenty of excitement, more than the kinds of adventures that most people would like to experience, especially in a place like the moon. I think that you'll recognize this photograph, which is the Apollo, his first step on the surface of the moon. I want to tell you a little bit about Apollo 12 launch. And I see that we're about 40 or so minutes into this, so I want to go a little bit quickly here. The weather conditions on this launch were very iffy. In fact, it had been canceled before because of bad weather at the Cape, but there was a window of clearing. And so Mission Control said, "Okay, we're going to send you up and out. You're clear for launch." They got a launch clearing, and 33 seconds after launch, Pete Conrad, who was the mission commander, was excited because the roll program had completed, and the roll program rotated the Saturn V rocket to clear the tower and not run into any of the hardware on the tower. At 36 and a half seconds, there's a strong crackle in the air-to-ground radar. And that crackle was that the spacecraft had been hit by lightning 36 and a half seconds after ignition. There were alarms all over the place. 3 fuel cell alarms went off. Both of the main direct current power buses alarms went off. The alternating current power buses alarms went off. It appeared that they had no electric power and no control over the power. The data was garbled because with the lightning strike, their transmission of data to the ground control was a complete malfunction. And then, of all things, there's a second lightning strike, and you can see it here. The lightning jumped from the Saturn V to the tower and then to the ground. And this is a photograph from the launch pad frame. When this was going on, this is called the 8-ball. It's a gyroscope. Normally, this tells you your position in space. This 8-ball was flying in all different directions. It was just unbelievable. So with the second lightning strike, this 8-ball is completely out of control. So the gyroscope isn't working either. The telemetry is scrambled, and there's all kinds of confusion. An engineer on the ground named John Aaron said to Pete Conrad, "Try SCE to AUX." Well, the transmission was garbled, and Conrad thought he heard FCE to AUX. And FCE is a fuel cell. And Conrad goes back to John and he says, "What the hell's that?" John repeated it, and Alan Bean understood that at SCE, which was the signal conditioning equipment, to the secondary power source. Bean flipped the switch, and at 1 hour and 50 and 50, or I'm sorry, 1 minute and 50 seconds. So they're about 24 seconds later, everything returns to normal because Alan Bean understood what to do and he flipped the switch. And I want to show you where that switch was, because that switch was in a place that you would never want to find it. It was way down. Oops. I'm sorry. I have to get the laser pointer here. Get the pen. That switch was right down here. And he knew where that was. He got a hold of it, flipped it, and everything was fine. Now, Apollo 13, not the movie. We all know that Jim Lovell was the mission commander. Jack Swigert ended up being the command module pilot, so he stayed in the orbit because Mattingly got sick. Actually, Mattingly didn't get sick. Mattingly was exposed to German measles. So when he was exposed to German measles, Jim Lovell said, I don't care if he's exposed, I want him. But Jim got overridden by mission control, and Jack Swigert ended up flying in place of Mattingly. Fred Hayes was a lunar module pilot, so Fred Hayes was in the position where Buzz Aldrin was, and Jim Lovell was in the same position in the lunar module where Neil Armstrong was. At 55 hours into the mission, there was an explosion. The movie has it wrong. So if you watch the Apollo 13 movie, you'll hear Tom Hanks say, Houston, we have a problem. Have, present tense. That's not what Jim said. What Jim said was, Houston, we had a problem. And what was the problem? They didn't know at this point. All that they saw was that their sensors were growing crazy. It turned out that there was an explosion in a liquid oxygen tank in the service module. Because Houston said to the mission commander Swigert, stir the oxygen tanks. Why did he want to stir the oxygen tanks? These were cryogenic tanks, which means that the contents, the oxygen in them, could be in a slurry kind of state. And if they weren't slurred, you couldn't get if they weren't stirred, you couldn't get an accurate assessment of how much oxygen was left in the tank. But now there was a wire fault. The wire fault inside the tank caused an explosion, and it blew out the side panel and also a second oxygen tank. So now oxygen that they would need for fuel cells and to breathe is no longer available. It's a big problem. So now the lunar module has to turn into a lifeboat. Because we knew that without the fuel cells to generate power and without oxygen, we were in trouble. We were in trouble because without electrical equipment on, it was going to get cold in the lunar module, and without oxygen, they could die from suffocation, but for lack of oxygen. But there was another problem. And the other problem was that the carbon dioxide in the cabin would go up, and therefore they could die from carbon dioxide poisoning or lack of oxygen or freeze to death. So it was a pretty dire situation. So we really had two problems to deal with. The one that I worked on was the one about freezing to death or suffocating. And the one that guys in Houston and also up in Bethpage worked on was how to get the environmental control system to get the carbon dioxide out of the air. This was a computer program problem that we had to solve. This was a physical and mechanical problem about how to reset things. So we reconfigured the computer model to be able to tell us what was going to happen inside the cabin on a return to Earth in the rescue ship lunar module. Because lunar module had to get them back. The command module had to be shut down because there was no power. And we determined that, in fact, if we could find a way to keep them alive, they would not freeze to death, and they would not suffocate, but it really meant that this environmental control system had to be able to get the carbon dioxide out of the air, and not just get the carbon dioxide out, but the crew members had to really slow down and rest so they were not metabolizing at an excited rate. But we knew that the mission was possible to save. So how did the mechanical part fix this? Because we knew from a mathematical standpoint that we'd get them home, but we had to be able to fix this. So in Houston and also in Bethpage, the engineers took all of the equipment that they knew was on the lunar module, threw it on the floor, and said, how do we reconfigure this system? Because the lithium hydroxide canisters, which get the carbon dioxide out of the air, were a different shape on the lunar module than on the command module. They were cylinders on the lunar module and they fit in here, and they were cubes on the command module. And how do you put a square peg in a round hole? So they worked on this and they came up with a solution. The solution was to take the cardboard cover out of the Apollo 13 flight plan manual. They had 2 lithium hydroxide canisters from the command module, a roll of gray duct tape, these are LEM guidance computer plastic bags that they used, and 2 hoses from the red spacesuits. The red spacesuits were the ones for the commanders, and these hoses ended up being put in place here. You can see, perhaps, and let me get a better pointer. You can see here, these plastic hoses had to rewire airflow to go through the canister and take the carbon dioxide out. They used 2 socks and 1 bungee cord to hold it in place. Necessity truly is the mother of invention. Just a word, as a chemical engineer, I have to go back to the lithium hydroxide canisters and tell you that lithium hydroxide combines with carbon dioxide to make lithium carbonate, which is insoluble, and water. The water gets recycled in the system, and the lithium carbonate falls out as a precipitate. So we got, as you know, we got them back. Tom Hanks produces a movie called Apollo 13, which happens, by the way, to be on Netflix right now until the end of the month. In the movie, Gene Kranz, who's the operations controller in Houston, says to the world and to the flight controllers, failure is not an option. I can't see all of you, but raise your hand if you ever heard this expression. He never said it, right? Never said it. The movie has it wrong, like it had a variety of things wrong. So how did this expression end up in the Apollo 13 movie? Well, a guy named Bill Broyles does an interview with Gene Kranz at his home. And Broyles asks Kranz, did anybody ever panic? Well, Kranz told him, no, nobody ever panicked. We just calmly laid out the options, and failure was not one of them. But that phrase was never even used. And so Bill Broyles now says, Eureka, I found it. This will be our tagline for the movie. Failure is not an option. So it gets into the movie. Kranz never said it, but there it is. I just want to have a brief memorial here to Jim Lovell. I met Jim, I knew him, my dad knew him when he was a test pilot flying supersonic airplanes in California. He died on the 8th of August this year at the age of 97. I have some stories about this, but we're sort of out of time. And I wanted to bring in a quote from Winston Churchill, even though it's old, it's completely relevant. October 29th, 1941, Churchill says, never give up, never give up, never, 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 in nothing great or small, large or petty, never give up, except to convictions of honor and good sense. And I'm sure that all of us listening to this quote today can understand how important this quote is, even in today's climate. So what did we learn? We learned a number of things. Computer processing power at its time was incredible. It had enormous complexity and unbelievable efficiency in order to run the computer programs. The dangers of our missions were often underplayed, especially to the public, that never learned some of these things that I spoke about tonight. Everybody contributed to the program, and nobody panicked. Everybody had a flight test frame of mind. Something goes wrong, you live in the here and now, you solve the problem. Those of us who worked on the program signed parchments, and photographs of our signatures were taken to the moon. This is the panel that is on the moon for Apollo 11. And so there were about 1,500 signatures here from the 3 different locations. This one is in Bethpage. This is at the Kennedy Space Center. This is at Mission Control in Houston. And so I need to give you proof that my name actually is on the moon. And so if we come up here, if you can see carefully enough with your computer screen, it says Doug Munch. That's me. And my name is on the moon with Apollo 11, Apollo 12. It would have been with 13, but sadly, we know what happened with 13. So I'd like you to read this silently. It will just take you 30 seconds or so. I think this is a very prophetic statement because as we did these, worked on our projects on the moon, and as we took this trip with the astronauts and look at the photographs that came back to us, it still remains an emotional experience for many, many of us and those of us who are still here. I know there are still stories that I can't tell because I'm so emotionally connected to them. It's just too upsetting. And so I try not to tell them except on very rare occasions. But here we are. The Apollo program was amazing. And I hope that you've enjoyed some of the stories that have come back. And it is not the end. Thank you very much.